Climate change and adaptation. First unit, Earth's climate system. So this is the fifth module, global greenhouse effect and global warming. So you know the main source of energy for this planet is sun, and solar radiation is radiant energy emitted by the sun because of nuclear fusion, and which creates electromagnetic energy, and the whole spectrum of the energy is close to black body. That means absorption emission is 100%, and is about 5800 Kelvin. That is, and half of the radiation is visible in short wave parts of the electromagnetic spectrum. So the radiation we are receiving is short wave parts. The amount of solar radiation that reaches any one spot on the Earth's surface varies according to the geographic location, that is latitude, longitude, time of the day, morning, noon, evening, and season, summer, winter, and local landscape means high altitude or low altitudes like mountain, terrains, and local weather, the existing weather patterns, clouds. So all the parameters decide how much sunlight we receive. And the sunlight, around 51% is absorbed in the surface itself of the earth, and this 51% get reflected back, around 4% reflected back on the surface. Rest of the around 49% are distributed among, reflected by the clouds 20%, reflected by atmosphere 6%, and absorbed by the atmosphere and clouds around 19%. That's how by overall the solar radiation's distribution takes place in the planet. Now let's talk about two planets. One is Earth and then Mars. Both of them are located almost similar location with respect to sun, but you can see all the location are almost similar, but Earth's temperature is around 15 degrees centigrade, but that of the Mars is 470 degrees centigrade. How so much difference? Because we have enough carbon dioxide to make our planet livable, but Mars there are 2 lakh times as much carbon dioxide as Earth. So what happens that it becomes a hot planet. It's not location. In fact, the temperature of the Mars is much more higher than the temperature of Venus, which is even further closer to Earth, because it is the carbon dioxide which makes the difference. In Earth, carbon dioxide is there, which livable conditions of the planet is maintained by that. But too much of carbon dioxide causes this problem. Do you need carbon dioxide? Yes, we need carbon dioxide, because the natural greenhouse effect is what caused by carbon dioxide, and that is required for the planet's survival. So it's a natural process in which solar radiations, which is warmed by the Earth's surface, again remits back in the atmosphere, and these gases, they are greenhouse gases, or carbon dioxide is one of the predominant gas among them. So they retain the temperature so that the planet will not get chilled. So the warmth is required for the sustenance of the livelihoods. But the right side of the picture you see, when you add more and more the carbon dioxide in the atmosphere because of our industrial activities and modernizations, which a lot of carbon dioxide added. In that case, what happens? More and more carbon dioxide layers makes the Earth hotter and hotter, because they don't allow the radiations back to the atmosphere. They keep on reflecting back, radiating back, so it becomes hotter and hotter. That is not a very good thing. And because in Earth, we have discussed before, there is very sensitive equilibriums existing between all the parameters, meteorological parameters, and the living organisms, biospheres. So now, if this is get disturbed because of the temperature variation, and temperature is one of the prime forces behind the wind, behind the sea, sea currents, and we have seen all these things. So and this will make a lot of differences in all the climate changes. That's why one of the major parameters behind the threat of climate change, threat of climatic change is this greenhouse effect, excess carbon dioxide. So the low frequency infrared radiations which emits low frequency, because but earth emits earth temperature lower than the sun's temperature, much lower than sun's temperature. Depending upon the temperature, the radiations are emitted. Since sun is very high temperature, so the radiation will be ultraviolet, short range. But earth is lower temperature, so radiation will be infrared, is mostly heat waves. And these have been trapped by the water vapors, like and carbon dioxide, methane. They are greenhouse gases stuffs, which prevents this to go out. But if there is no greenhouse effect at all, what will happen? If it's so bad thing, then what will happen? No, it's not bad thing. If there is no greenhouse effect, then earth temperature would have been minus 18 degrees centigrade. Imagine how low it is. It's the greenhouse effect which makes our temperature livable. 0 degree itself is ice. Minus 18 degrees centigrade would have been the planet's temperature if there is no greenhouse effect. Then what is this greenhouse effect? Why this name given? Usually they have in western countries and cold countries, temperate climate, because of the too much chilling, the plants dry up. So to grow the tropical plants, they create a glass structures. So the glass is like greenhouse. So the glass house are called greenhouse. What it does, it prevents the radiations go back, because it reflects back into that. So the inside the greenhouse or glass house, the temperature is much more warmer compared to outside. So many of the tropical plants can also be grown there. So this effect, this type of glass house or greenhouse has been practiced in many countries. So when the whole planet become like that, it become greenhouse effect. It's just the entire planet is something like kept inside a glass house. So this is what the schematic diagram of greenhouse effect. Long wavelengths of infrared, which is coming back, this red color is reflected by inside. And solar radiation short wavelengths infrared lights, it is number 2, which also when it comes inside is also trapped inside. And this visible light, of course, number 3, it comes and goes back. It doesn't get affected by the glass. Glass is transparent for that. So this is how the greenhouse takes place. Practically, we have experienced that too. If you go a vehicle, car, you have seen that inside the car, if you don't put the AC and everything glass, you find temperature much hotter than outside. There is also greenhouse effect. If you see the readings, one of the latest readings of carbon dioxide in Mauna Loa Observatory in February 12th, 2019 is 411.87 parts per million. How does it matter? Is equivalent to 1% increase in the power of sun. You can see over a period of time from 1960s to 2019 there is a increase trend of the temperature. So now it's 411.8 ppm, and as it going in increasing, so this increase from 1960 to 2015 is almost 1% increase in the power of sun. Can you imagine what is the meaning? And it should definitely be contained within 450 ppm. If it's going to more than that, it will be major disasters. And this leads to global warming. What is global warming? It is the global temperature rise with respect to pre-industrial times, before industrial times, because most of the carbon dioxide emitted after pre-industrial revolutions only. So pre-industrial time, the global temperature, if it rises beyond that, the pre-industrial level, the period of time before the start of industrial revolutions. So IPCC special report uses the reference period of 1850. So this is Interplanetary Convention on Climate Change. So 1850 to 1900, that is before industrial revolution. From that standard we are comparing. There is a base level. Warming is defined as the increase in 30 degree global average of combined air temperature over land and water temperature at the ocean surface. So this is the average for last 30 degrees, like a moving average. So 30 degrees is calculated. So next 2 years comes, then again 1 year goes back from the bottom and 1 year goes on top. So this is 30 degrees moving average calculated. So the average temperature in land and water temperature, water surface temperature. So that is the average temperature considered for the planet. So there is an increase in global warming. So human induced warming reaches 1 degree centigrade above the pre-industrial levels around 2017. There is 1 degree increases compared to 2017 compared to the previous. That means 1985, 1850 and 1900, that range we have 1 degree increase. If the pace of warming continues, we will reach 1.5 degree around 2040. Means what is the meaning? 4 degree, 2 degrees, 1.5 degrees, 1 degree. What is the meaning? The small degrees. So this is just a summary of the greenhouse effect, the how and global warming. Because of that, the same thing about to discuss the reflection, radiations, how the whole planet is maintained. Now coming back to why is so important about the 1 degree centigrade. What was the average temperature, global temperature in the ice age, when the whole planet was almost covered with ice? It's just 7 degrees centigrade lower than 2019. Just imagine, just 7 degree fall itself, the whole planet become ice. And how much that one? That was 7.8 degrees centigrade. It's not zero. Not zero. So just 7 degrees centigrade is sufficient to make the whole planet ice. So 1 degree makes 1/7 of that at least. So these are some of the effects of if the temperature is 2 degrees centigrade of warming, heat waves up to 1.5 months, and 1.5 degree it will be 1.1 months. If fresh water, it will 17% increase, and scarcity, and it will be 9% scarcity, 1.5%. If 2%, heavy rainfall will 7% increase, and 1.5% 5% increase. Crop yields, similarly crop yields also you can find the variation of crop yields, decrease in the crop yields. The sea level rise, 50 centimeter increase will be in 2%, and 40 centimeter 1%. And coral bleaching, the coral reefs are bleaching, 98% bleaching will take, 98% bleaching will take place too, and 90% 1.5 degrees. So you can see just 1.5 is some marginal increase that we may be able to sustain. 2.8 is very high. So that's the reason why we want to ensure that it should not increase. Our target is at least to make it less than 1.5 degrees centigrade by 2040, and gradually try to make it zero increase. That is the whole target. And this is the present status of that. 2016 we have a current annual emission 52. This is the carbon dioxide equivalent, okay, in the greenhouse gases, gigatons carbon dioxide equivalent, GTCO2e. This is how we express the greenhouse effects. So where emission are headed, it will become 58 by 2030. And what we want, it should, if it's 1.5 degrees centigrade increase, then it will become 25 to 30. That much production is required to ensure that, because increasing, to ensure this much greenhouse gas productions to 30 gigaton carbon dioxide equivalent, to ensure that 1.5 degree increase. And what is the meaning? It means net zero emission consider 1.5 to 0. That means presently you have to make 0, then only the existing things will come back to 20 to 25 to 30, and then only the temperature can be maintained 52 to 58. Temperature can be reduced from 50 to 58 to 25 to 30, and that is what the target. How will 4 degrees rise affect our daily day to life. If it increases 4 degrees with present status, the behavior of insects will change. And the productions of all the crops, here we see coffee, will decrease. And body temperature increase, less heat dissipations. Warmer air can hold more water vapor, because we studied about that. Warm air can hold more water vapor, so there will be more rainfall, and at the same time more scarcity of water because improper distribution of water, and many more. Here are some snapshots of the greenhouse gases and global warming. How the temperature profile of the whole planet changed over the last 50 years. This increase is red color by 4 degrees, a decrease in the bluish color, and the observed temperature. And human driven activity is the main cause in the observed temperature. As you can see that the red color, we saw that. And natural drivers will not increase so much. The variation will not increase so much. The right side of the top picture. And below the carbon dioxide emission by source, different years. So who is contributing mostly? The coal, oil and gases are the most contributors of that. And different countries distribution. India of course less compared to that. And United States tops in the list. So this is what affects the global warming because of greenhouse gases. The temperature 2090, if carbon dioxide emission drops by 0 by 2080, this is what plant will look like. This was expected. Otherwise, if we don't do that, plant will look like the bottom pictures, completely red. So there's more details about this global warming effects. What are the causes? Agriculture activities, fossil fuel combustion, deforestations, all the things can contribute. And then what it leads to? It leads to ocean acidifications. Then global warming can also lift environment, habitat destructions, ecosystem collapse, biodiversity loss, intensification of extreme weather events, glacial retreats, freshwater loss, coral bleaching, sea level rise. And for human beings, it can affect the human flooding in the cities and farmlands, which can also lead to human migrations and conflicts, crop failures and farmland loss, direct physical harm to human beings. And the feedback is which causes the global warming more and more. So snow covers reductions, reduces sunlight reductions because the albedo changes. Then atmospheric water vapor increase, and permafrost, tundra areas and polar areas, permanently frozen ground, permafrost melts, and that again releases methanes which are trapped, paleomethanes, old methanes. So they again goes back to further greenhouse effects. Methane contributes to that. So this way, the whole imbalances of the planet changes and becomes more and more unstable. So now we'll see a small clipping which explain a summary of what I just discussed.
The Earth gets heat from the sun. In the atmosphere, greenhouse gases like carbon dioxide trap this heat and keep it from escaping back to outer space. Trapping some heat in the atmosphere is a good thing because it keeps the planet warm enough for us to live. But there's a problem. People all over the world are adding extra carbon dioxide to the atmosphere. That's because today we burn fossil fuels like coal, oil, and gas to do many of our everyday activities, like driving our cars, using our computers, and heating our homes. All of this extra carbon dioxide is trapping more heat in the atmosphere, making the Earth warmer and causing other climate changes too. The signs of climate change are all around us. Temperatures are getting warmer, giant ice sheets are melting, and the oceans are rising. In many places, flowers are blooming earlier, snow is melting sooner, and birds aren't flying as far south for the winter. So why does this matter? Well, if the planet keeps getting warmer, we can expect more powerful storms and more flooding, droughts, and heat waves. And these changes could cause additional problems, like the spread of certain diseases, more wildfires, and food and water shortages. Climate change could put entire ecosystems, like coral reefs, in danger, and many plants and animals could become extinct.
Now, what are all contributes to greenhouse gases? It is not just a matter of carbon dioxide. You find the whole range: methane, nitrogen oxides, hydrofluorocarbons, then perfluorocarbons, and recently addition sulfur hexafluoride. Recently we discovered that also, which is from the TFT monitors of the computers. So all of them keeps on adding to greenhouse gases. Now how do we compare them? So it is important to distinguish between what 1 unit of carbon dioxide emitted and 1 unit of carbon dioxide in the atmosphere stock. How much release, how much emits. So not that every unit of GHG greenhouse gases emitted stays in the atmosphere forever. There is half-life, just like radioactivity, radioactive elements, half-life by the time by which half of the total matter get decayed. Similarly, within half of this GHG decaying time, it differs. So there is a standardized tool used for all other greenhouse gases in terms of carbon dioxide equivalent. Based on what? Based on the ability to absorb the energy and how to radiative efficiency, and how long they stay in atmosphere. Based on the two parameters, greenhouse potential is estimated. This is a list of the greenhouse potential of this greenhouse gases, GHG. Carbon dioxide, if you consider 1, so methane is 56. So global warming potential for methane is around 12. If carbon dioxide is considered 5, it means about 12. And nitrogen oxide is 120. So this way, and HFC, which is as a freons and refrigeration, 264. Sulfur hexafluoride 3200. Perfluoromethane 50,000. Perfluorethane 10,000. So now you see, and how much time is required per half-life periods. In 20 years, this much. This is given the right, and 100 years and 500 years. Now even after 500 years also, so many so much is will in the atmosphere. So this is how you quantify all the different greenhouse effects and greenhouse gases potential. And what it leads to? It leads to change in the carbon cycles. You know, the carbon cycle is always maintained, the whole planet is sustainable, because the carbons from the animals or the plants, they decayed back, and those carbons, when as a fossil fuels, they come out and combusted, become again carbon dioxide in the atmosphere, which is again taken by photosynthesis by the plants by respiration. And animals and plants also give the respiration of that, and decaying organism might also give respiration for that. Giving carbon dioxide back to the atmosphere. So this whole cycle is maintained like this. Now if the cycle gets disturbed because of the greenhouse effect, because of the industrial activities, and which leads to greenhouse effect, which leads to climate change, and primary of them is global warming, then we will be in very endangered situations. These are the different sources from which your carbon is contributed now presently, which is not a basic part. It is so it destabilizes the whole balances, equilibrium in the carbon cycles. And there is a destination. And so what has to do? He will go to increase there. It has to go to atmosphere, it has to go to plant growth, it has to go to dissolve in oxygens. So the plant growth and the soil and dissolved oxygen is almost constant, because there is not much variation in that parameters in those land use areas and land use land cover. So naturally it has to go to atmospheric uptake, and that's exactly what is the main problem. Thank you.